Assalamualaikum everyone. Welcome to my physics tutorial for high school students. Today's episode is a revised excerpt of a past upload on vision defects, myopia, and hyperopia. So, what's the physics explanation in correcting nearsightedness and farsightedness? Find out, stick around, watch and learn. The question is, a certain farsighted eye cannot see objects distinctly when they are closer than 1.00 meters away. Find the focal length and dioptic power of a correcting lens that will enable this eye to read a letter 25.0 centimeters away. Question letter B. A certain nearsighted eye cannot see objects distinctly when they are more than 25.0 centimeters away. Find the focal length and dioptic power of a correcting lens that will enable this eye to see distant objects clearly. A normal human eye can see distant objects and near objects distinctly because the image of the object is exactly formed by the eye lens on the plane of the retina. We say that this eye is a normal eye, right? When the lens of the eye allows incoming light to focus in front or behind the plane of the retina, a person's vision will not be sharp. If the eyeball is too long or the cornea is too sharply curved, the rays are focused in front of the retina. Alright? Hence, the vision is blurred. And this vision defect is what we call myopia, or the person has a nearsighted eye. Right? If the eyeball is too short, or if the cornea is not curved enough, the rays are focused behind the retina. And so the vision is also blurred. A defect known as hyperopia. Or we say that the person has a farsighted eye. In answering question letter A, we need to define what a near point is. So, a near point is the point nearest the eye at which an object can be placed and still produce a sharp image on the retina. Like in the problem, the farsighted eye cannot see objects distinctly when they are closer than 1.00 meters away from the eye. Alright? Hence, the near point for this eye is 1.00 meters away from the eye. If the object is located, for example, 25.0 centimeters away from the eye lens focuses the rays behind the retina. Alright? Because it so happens that the eyeball is too short or that the cornea is not curved enough. So the rays are focused behind the retina instead of on the plane of the retina. And this results to a very blurred image. Alright? And this kind of eye defect or vision defect is known as hyperopia or farsightedness. And how do we correct this vision defect? You will find out in just a short while. We emphasize the given data. The near point, which is 1.00 meter, is considered the image distance, di, which means the corrective lens to be used here will form a virtual image exactly at a distance of 1.00 meter. Alright? And that is why we indicate di here with a negative sign because it is a virtual image. Now, the object distance do is given as 25.0 centimeters or 0.250 meters. And our target variables are the focal length of the lens as well as the power of the lens, okay, denoted by capital D. All right. So we set up the thin lens formula. The formula 1 over f, or the reciprocal of the focal length, is just equal to the reciprocal of the object distance plus the reciprocal of the image distance. All right. So when we substitute later, we are expecting that the unit for the focal length, of course, will be meter. Now, for the power of the lens, capital D, all right, it's just equal to the reciprocal of the focal length when the focal length is expressed in meters. So, executing our formulas, all right, for the focal length, small letter f, we just substitute, all right, the given quantities, uh, the object distance, which is 0.250 meters, and the image distance, which is negative 1.00 meter. So when we simplify this equation, all right, we will get the value for the focal length equal to positive 0.330 with three significant figures. All right, that's in meters. And this implies that the correcting lens is a converging lens. All right. A converging lens is a type of lens where the geometric center is thicker than its edges. All right. So calculating for the dioptic power, we have capital D, which is the reciprocal of the focal length. All right. That is, we divide 1 divided by positive 0.330 meters. So our answer for the dioptic power, capital D, is positive 3.03 diopters. All right. Diopters is the reciprocal of the unit meter. All right. So this value for the dioptic power means that your eyeglasses, all right, need 3.03 diopters of strength to correct the vision defect, which is hyperopia or farsightedness. So we emphasize that a converging lens forms a virtual image, all right, a virtual image of the near or close object at the near point of the farsighted eye. Take note, all right, the converging lens creates a virtual image of the close or near object at the near point. And in this problem, the near point is equal to 1.00 meters. All right. So when the rays from the virtual object, all right, um, the virtual image formed by the lens, all right, by the correcting lens, becomes the object. Okay, becomes the virtual object of the eye lens. So when the rays from the virtual object enter the eye, most of these rays are refracted at the cornea. The eye lens, which is always considered a converging lens, all right? The eye lens contributes only about 20 to 25% of the refraction, but its function is important. With the help of the converging lens, all right, the eye lens is able to form the final real image exactly on the plane of the retina, so that the hyperopic person can now see a sharp image of any close or near object. In answering question letter B, we also emphasize the meaning of a PowerPoint. So a PowerPoint is the location of the farthest object on which the fully relaxed eye can focus, right? As stated in the problem, the nearsighted eye cannot see objects distinctly when they are more than 25.0 centimeters away. Therefore, 25.0 centimeters here is the distance from the eye known as the PowerPoint. Objects located beyond this PowerPoint will appear blurred to the naked nearsighted eye, right? This is because the eyeball is too long or that the cornea is too sharply curved. Hence, the image of any distant object is focused in front of the retina. Alright? So the question is, what type of correcting lens should this myopic person wear? We will find it out in just a second. Distant objects are assigned an object distance equal to infinity. Alright? The image distance di is equal to the power point, which is 25.0 centimeters or 0.250 meters. But then again, this image created by the correcting lens is virtual. Hence, we have the negative sign for the eye. Again, we are looking for the focal length f and the dioptic power of this lens. The same formulas will be used, alright? For finding the focal length, we just use the reciprocal formula. And for the dioptic power, still the same formula. Capital D is equal to the reciprocal of the focal length, provided the focal length is expressed in meters. So substituting, alright, into these formulas, the reciprocal of F, alright, equals 1 over infinity plus 1 over the image distance, which is negative 0.250 meters. Alright, we know that 1 over infinity is equal to 0, so the focal length f will simply be equal to negative 0.250 meters. And this implies that the lens is a diverging lens. And we know that the diverging lens is thinner at its geometric center, okay, than at its edges. So, moving on to our calculation for the dioptic power, capital D, alright, 1 over F, we substitute 1 over negative 0.250 meters, alright, and we get the dioptic power of this lens equal to negative 4.00 diopters. And finally, we emphasize that this diverging lens forms a virtual image of the distant object at the far point of the nearsighted or myopic eye. And of course, the eye lens in turn will create the real image on the retina, right? Enabling the myopic person wearing this diverging lens to see a sharp image of distant objects. So that concludes our discussion. Until the next episode, inshallah. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.